Okay. So we're going to keep going on the magnetic field. Where are we? That happened. Oh no. Oh, good Lord. Let's not start the semester over. All right, that happened, yes. Exam review last time, catching up on magnetic field. So now we're going to, today, finish sources and get into forces and torques. We're like half a lecture behind. Not too bad. So this is all coming up. We're in chapter 29. If you're reading at home, remember you can always use these section numbers to know exactly what we're covering. Pretty much exactly. Okay? So, last time we talked about the Biot-Savart law. And we talked about it in general. We wrote it down. And we talked a little bit about it, the right-hand rule. So now we're going to use it to get the magnetic field of a long, straight wire. Okay? So we're going to, in this class, use the field of three different geometries. We're going to do the long straight wire, the loop of wire, and I forgot what it's called. One of these. I blanked on the word. A coil of wire. And in every case, wire means current. It's implied that the wire has current going down it. Otherwise, it would have no field. Okay, so it's just really cumbersome to write a wire carrying current every time. So from here to the rest of the course, wire implies current. Okay? Now, this first one is actually really hard, long derivation. Okay? We're going to do it just, I want you to understand where this comes from, that I'm not just making it up. I could just write down the three formulas and we could leave, right? And if you want to, you can leave and it'll be on the video, the three formulas, or they're in the book. But I thought, why don't we go through and just get a flavor for the vector calculus and see where these things come from. The first one's actually the hardest. The next two won't be so bad. But let's just be bold here and really go through it. Really blow our brain out here. Meaning use it too hard. So current going down a wire like that. There's your wire. There's current going down it. And we want the magnetic field, say, here. At some distance along some vertical direction from the wire. So the wire is really long means, in physics you've got to think about when they say long, what do they mean? In this case, we're calculating as though the wire were infinite, right? Infinitely long. So the scale you care about is that this is long compared to that distance. Okay? Not required to be able to do the problem, but just it's good to start thinking that way. So what we got to do is think about, what did Biot-Savart say? It said that it's a differential field. And you got to think about the differential current. We got to add it up. All right? So it was mu naught, the permeability of free space over 4 pi, just constants. The current in the wire, yeah, that makes sense. And then times ds crossed with r hat. Like that was the ugly part. And then over r squared. So that's what made it hard, is it's got a cross product in the differential element. Right? How do you deal with that? Can we watch the cocaine on banknotes video? Yes, that is why I have it open. That is what we were going to watch. Spoil the surprise. 713-806-1961. There you go. We will talk about cocaine today, and you will be responsible for all the nicknames of cocaine that they list. So you better start watching Miami Vice, because it's going to be a lot to cover. Okay, so that tells you dB. So now we've got to think about how we're going to deal with this cross product. Well, we're going to use the right-hand rule. So let's think about, where is ds? ds means we add up a bunch of little pieces of the wire. Okay, so I'm going to draw one over here. This is a little piece of the wire, and ds is just a little piece along the current. So ds is an element along along the current, right? So you can imagine if this were some curved wire, we would break it up into a bunch of little ds vectors like that. R, here we have the magnitude of r. Here we have the unit vector in the direction of r. R is basically from the current element to the point you want the magnetic field at. All right, the point at which you want the magnetic field. So it looks like that. Now where's r hat? Oh, sorry, that's r. That's r vector. So r hat is just the unit vector in that direction. Often it makes you feel good to draw a unit vector short like that, because it implies that the length is longer than the unit vector. The length could be shorter than the unit vector. There's something about making it short that makes you remember that it's equal to 1. It could be this could be 1, and this could be a half, whatever. The unit vector is the vector along the direction of r with a magnitude of 1. I've said too much, as usual. Okay, what are we going to do here? The hardest part to deal with is clearly ds cross r. But let's go ahead and think about, let's think about the direction. Let's do it this way. Let's go ahead and just write b. We're going to just solve for b. All right, how are we going to do that? We're going to add up all the little db's. How are we going to do that? We're going to add up all these. Right? But we've got to think about the differential element. Whenever you've got to integrate something, you say, what's the differential? It's ds. We've got to add it up for all the little ds's. Do we really want to do it for ds? Well, we'll decide in a minute. For now, let's just write it down. Let's integrate all the permeabilities of free space, the current, the constants, 4 pi, those are all constant, right? And now we've got to write ds cross r hat, or r hat. Yeah, so what are we going to do with that? Let's start simplifying it. Let's draw over here, because I have room, the vectors independent of everything else. Here's ds that way. Here's r hat that way. All right. So why don't we go ahead and define an angle? We're going to call this one phi. Is the angle between ds and r hat. And we want to write that angle there because as we change ds, phi is going to change, isn't it? Right? Phi is here. Phi is 180. And way over here, phi is almost 0. Right? ds this way, r hat that way. Teeny phi over here, big phi. So we can think, if we write this in terms of phi, maybe we'll integrate with respect to phi. Or maybe we won't. Let's go ahead and write it down. So the cross product is magnitude times the sine of the angle between them is the magnitude of the cross product. So let's write that down first. The magnitude of ds is ds. Oh, there's your scalar differential element. What is the magnitude of r hat? Somebody shout out a number. The magnitude of the r hat vector. 1. Very good. You guys are rocking. And what is the sine of the angle between them? Sine phi. Sine phi. There we go. So there's the magnitude of ds cross r. Let's put it over r squared. All right. And technically this is a vector, so we need a direction. Get it out. All right. Get that right hand out. Unholster it. Take the safety off. Here we go. Okay. So we're going to say ds cross r. We're going to put our fingers along ds. Right? And we could do like that. Oh, I can't curve it to r that way. What if I put it? I can't curve it to r that way. It's like this. If I put it like that, I can curve ds to r. And we see that the cross product of ds cross r hat is out. So I like to write silly things like this. Out hat. Right? We don't have a coordinate system set up, so just call it out hat. It's just the direction. What is the magnitude of out that's going to affect this answer? Nothing. The magnitude is 1. Right? So that's the point of a unit vector. Out hat. All right. So now we have a beautiful integral. And this is sort of the problem in physics a lot, is we are going to want to do this integral. And we got to say, as we move along different sections of the wire, we got to integrate with respect to all the things that are changing. So what all is changing? Where'd theta go? Well, as you move through, phi changes, right? As you move along, phi is different. But what else is different? R is different, right? As you move along, R changes as well. So to integrate it, we got to get everything in terms of one variable. So we just got to write those in terms of the same thing. I don't remember why, but I did this in terms of theta. It might be that mathematically that's the only way to do it in 2 steps. It might be I'm being dumb. It'd be easier to do it in terms of phi. I honestly don't remember. But let's do it in terms of theta. So let's convert r to theta. Let's convert. We've got to convert ds, the magnitude ds to theta. Not that ds actually changes, but it affects other parts. It affects things. Don't worry. And then we've got to convert phi to theta. Got to convert all those to theta. And then we can integrate it over some new limits. Why can't you have your thumb point inward? Also, isn't the angle from dB to r hat always something? Okay. If my thumb points inward, can I curve my fingers from S to R? No. Because you have to go counterclockwise. That's why. Yeah. Because by definition, I guess I could do that, but I get nauseous and vomit in front of everybody, and I had 3 donuts this morning, okay? So you curve this way. Typically, the definition is you go with a smaller angle. You go with the one that's less than 180. Also, it's a good idea to go with a positive angle. ds to r by the smaller angle is the direction of the cross product. I am 99.9% sure. But yeah, don't try to break your fingers, okay? Okay, so we want to make all these conversions. So we look at it and say, oh, well, clearly sine of phi is cosine of theta, obviously. Not obviously, but if you did enough geometry, you would be able to tell that, well, one, you can just use trig and say, well, the sine of this angle is the opposite. It's the high part, and the cosine, it's this. This is the sine of phi and the cosine of theta. Or you could say this angle, x, is 180 minus phi, but it's also x plus theta is 90. You'd get there, okay? So just trust me. When this angle gets really big, this angle gets really small. That's why the sine of one is the cosine of the other. So that's just from geometry. And then, how do we deal with ds? We've got to say s equals y tangent theta. What was y? I always forgot to specify what y is. Y is this. Why do we call it y? Because we're already using d and r for other things. So I'm calling it y. Okay? So you can see that s is the position along this axis. Right? So that's this length of the triangle down here. Yes, that's why we need ds. I'm sorry. It's not really that we're thinking of getting ds to theta. It's that we also have to deal with s moving around. Yeah, let's get s to theta. There you go. That's technically, mathematically why we're doing this. Blanked out for a minute. Is as you move it along, you're in different positions along this axis. Yeah. So, so tangent of theta is opposite over adjacent, so s is y tangent theta. Okay, so that's how we get ds, is you got to look up the tangent of, or the derivative of tangent and say ds d theta is y over cosine squared theta. Yes, the y is a constant. The derivative of tangent is 1 over cosine squared. Yes, remember trig in like 8th grade? Yeah, you got to use it. Okay. And then r is y over cosine theta. So you can see there's no physics here. This is just the difficult algebra and geometry you have to do these problems. Okay? You don't have to do it. I just want you to see that it's all there. It all works out in the end. I think if I show you that this all works out in the end, you'll be more comfortable with the answer. I think otherwise, it would have been the constant questioning. Nobody likes that. Right? I don't like to be questioned. If you want to know one thing about me, it's that I don't like to be questioned. Let's see. Okay, so what are we doing here? What limits do you think we want to integrate from? When ds is way over here, that theta is becoming practically 90 degrees, right? Oh, this thing is so far away, this is practically flat. So that would be minus, let's call it 90 because, you know, we're not sophisticated. All the way over here where it's plus 90, like that. So if we're going to integrate with respect to theta, that's what we got. So mu naught I over 4 pi is constants. Mu naught I over 4 pi, all right? Let's see. I've got all these terms written here, all pretty. I've got y over cosine squared theta. That is ds, right? D theta there, right? So the ds is y d theta over cosine squared theta. Nice. Then I've got cosine squared theta over y squared. Let's see, which one is that? Oh, that's the 1 over r squared, right? Cosine squared theta over y squared is the 1 over r squared. Very nice. I love this so far because it's actually working. And then we have cosine theta. All right. Okay. So this is this just converting everything to theta. So that when we do this integral from minus 90 to plus 90, all the terms that vary are going to vary properly. And we'll get maybe the right answer. Let's see. Looks like we've got mu naught I over 4 pi y. Let's see, we're going to do the integral in our heads. Prepare. Right, and what is the integral of cosine from minus 90 to 90? It's 2 pi. No, it's 2. Yes. Yes, because integral cosine becomes sine. Sine of 90 is 1. Minus sine of minus 90 is minus 1. 1 minus minus 1 is 2. So it's 2. So there's your cosine integral. Do it on your own time. I got to fit this on one board. So then the answer is mu naught I over 2 pi y. Or you might see it written as like R, mu naught I over 2 pi, how far away you are. If you say I'm R away, it's mu naught I over 2 pi R. But we used R for this. Right? If you say I'm a distance A away, it's mu naught I over 2 pi A. If I'm a distance D away, it's mu naught I over 2 pi D. Right? But that's just the form of how the magnitude changes. Should we understand what's going on, or is this going to like end in a formula or something? I'm 100% lost. Okay, just done, yeah. So as I said, this was just to let you understand where these formulas come from, right? So this is something that if you were like, getting into field theory, you would want to be able to follow every step of. And I didn't want to just give you the formula because then nobody believes me. Everybody thinks I'm worried, really. I'm insecure and think people will think I don't know where it came from. So I'm just showing you that I know where it came from. What is mu naught? Mu naught is the permeability of free space 4 pi times 10 to the minus 7 units. Okay. Is mu naught. It's just a constant. It's in the front cover of your book. I think the definition of deflection is there also. I'm not sure. Okay. Let's see. So now we're going to use it. Now we're going to talk about what it means. So those of you that had no idea what that was about and are 100% lost, now pay attention. Here we go. So let's draw what this field looks like. Okay? So here we go. We say, here's our big wire. Okay? And we're going to use, did I want to do this here? Let's see. I thought I had a whole page for this. Yeah. Okay, yeah, we're going to draw it here. Okay, here we go. So here's the wire, current going to the right, just like that. We just solved for the B field, and we said it's coming out of the board, right? So we got some value here, like that. And I'm drawing a big dot. That's the vector coming out of the board at your face. Big dot means it's a big field. What if we go farther away? It's a 1 over R, right? So the field gets smaller as you go farther away. Like that. So B, magnitude, goes as 1 over R from the wire. Okay, well, what if I moved over here? Well, the wire's infinite. The answer doesn't really care about moving to the left or the right. From wire and constant along wire. All right, so you see here I'm saying 1 over R perpendicular to the wire, your radial distance in a cylindrical coordinate system away, constant along, because it's infinite. There's no reason it would vary as you go down the wire. It's that magic symmetry idea. So you can kind of visualize it like that. And for a lot of problems, it'll be important to be able to visualize and think about how does the field vary with distance. Now, what about below the wire? What on the other side? How would you draw this? Everybody do your right-hand rule and think about how you would draw it. Okay, I'm going to draw mine secretly, and then we'll see if we match. The crochet. Okay, so it's going to be kind of like this. You're all drawing, right? Yes. Everyone's drawing independently. It's like kindergarten. We're going to draw, and then we're going to watch a movie. Let's see. Okay. This is the kindergarten I went to. I don't know what's wrong with you people. This was pre-K where I went. Does yours look like that? Oh, I did 4 on top and 3 on bottom. I feel asymmetric today. So let's think, if we were going to say, what's the field down here? ds is that way, but now r is that way. Here we go. ds cross r, your thumb goes in. Sorry. Right? So the field on this side is into the board. But up here was out of the board. ds cross r, it's because r is the other way. See? So ds is the same in both cases, but if you're going to curl your thumb up to r, you get these. And if you're going to curve it down, you get those. Right? That's why it's opposite. I drew the big X's to say the field is big and it goes down as 1 over r. Okay? So what you get is a cylindrical field. If we had to draw it in 3D, hold on, here's one of my 3D drawings. This was first grade. Here we go. You get, we said that, let's see, it would be coming out of the board here. Therefore, it must be kind of going down. Oh, that's horrible, like that. So it's going around. If we were going to draw it as a line, if we had done field lines, it'd be like that. It's a cylindrical field going around the wire like that. We didn't really do field lines, but I think you get the idea. Oh. Right? Out here, they're coming out of the board. Here, they're going into the board. So when you see a wire carrying current, you want to start visualizing a magnetic field swirling around it. What direction does it swirl? Right-hand rule direction. Let's see. All right. Turn this off briefly. Here we go. Okay. Yes. Okay, so now what we're going to talk about, though, so this was kind of a hard way to figure out which way the field is. We had to do a right-hand rule cross product. There's easier way. So now I'm going to show you the other right-hand rule. It's easy to use if you trust it. I don't know if you're going to trust it or not. I'm going to show it to you. Okay, let me just write, just so you'll have it yet again in your notes. The magnitude of B here that I've been drawing is mu naught I over 2 pi r. You might want to start like memorizing that. That's like one of the fundamental ones to memorize. Mu naught I over 2 pi r. It will be on the equation sheet. Okay. Let's go back to the right-hand rule. We talked about it for cross products, but often in physics, one quantity is curved and the other is straight. Because opposites attract or something like that, okay? But you can use a right-hand rule in any case like this. You don't have to actually think about the cross product, okay? So what you do is your fingers are the curved part, obviously, because your fingers can, well, obviously, your fingers can curve, and your thumb is the straight part. And you say, always? I mean, are you sure? Always? Yes, always. How can I be sure every time in physics something is curved and something is straight that it happens to fit your right hand? How do I know? Because we set it up that way, right? When we set up all the laws, we can put a negative sign wherever we want. The first person to write the law gets to pick the negative sign. Stupid Benjamin Franklin screwed it all up. But since then, we've had it all correct. Okay, we've always kept them consistent, and this is always true. So, for example, current flowing that way. Ooh, right? You could think, oh, ds is the other way. I got to do a cross. No. Which one is curved and which one is straight? The current is straight. So you don't even do them in this order. I know the current. I want the curvy part. The current is straight. I'm going to put my right hand thumb and say, oh, it goes like this. I mean, don't hurt your fingers trying to go into the board. But you get the idea. It's going around. Therefore, this must be like that. It still goes down as 1 over r. It's just that this doesn't tell you that. It's just telling you the direction. And then you would know from witnessing this brilliant lecture that it drops as 1 over r. Right? Like that. So just the direction. One thing's curvy, one thing's straight. What about this? Here's more practice. Oh, current going down a wire. You can do your right foot also. There's a way. I'll show you sometime. I do cross product yoga. Down. Which way is it going? Sometimes you have to get up and go on the other side of the drawing. So if in the exam you have to get up and get on the other side of your little desk, that's okay. Like I've seen people have to do that before. It's funny. Okay. So thumb along the straight part goes in on the left. And it comes out on the right. Oh, too many donuts this morning. There you go. Yeah, like that. We could do the cross product if you really wanted to. ds cross r. ds cross r. Out. Yeah, there you go. ds cross r. You can always check it with the cross product if you want. But the whole point is it actually makes it easier. And it's not just the magnetic field. What if we had something spinning, like this disk? All right? And I tell you, its angular velocity vector is that way. I don't remember if we treated angular velocity as a vector or not. I don't remember how detailed we did the mechanics. But angular velocity is a vector, and the direction it points depends on the nature of the rotation. But you don't have to think about all that. You just have to say, the angular velocity vector is straight. Which way is it curving? It's going around that way. This is going around like that, and it's coming around like that. Right? It's going around like that. Like that. And even for torque, we're going to do torque because the magnetic field requires you to do torque. So let's imagine we have like a big rod here and a string with a mass on it. All right, and it's connected here. It's like, a pendulum or something. And we release the mass. Hopefully, either you took 125 and you have the prereq enough to know it's going to fall. Right? There's going to be a force that's going to make it fall. So the question is, which way is the torque? All right. So the torque is the straight part. It's a vector. Right? Vectors are always straight. And then the curvy part is the direction of, technically it's not the motion, technically it's the angular acceleration. Okay, technically. If you release it from rest, those will be the same direction. It'll move around this way. Angular acceleration will be around this way. But if I threw it up like this, technically it would be accelerating this way, moving that way. But let's not re-litigate all that pain from 125. Let's just say we release it from here. And I'll say the motion. Releasing it from rest, it's going to go that way. So which way does that torque correspond to? Oh, my fingers just go like that. With the motion, it must be that the torque is into the page. Okay. By definition, that will always work out. Okay. Anytime you have something curvy and something straight, it'll always be the same. Where are we? Oh, no, okay, that was somebody's old question. Something about juice. Yeah. Okay. Okay. Yeah. Oh, that's also old. I'm sorry. Why can't is W work on the board above? Oh, there's no work. That's an omega. That's a lowercase omega for angular moment or for angular velocity. Lowercase omega. Okay. Okay. So right-hand rule. You can also use it that way, and we're going to have more magnetism cases where you would use it that way. So we'll get to them. Okay. We've done one geometry. We've done the field around a wire. Now let's do the field at the center of a current loop. Is another fundamental formula that you must know. Okay, so I'm going to draw, so the field, we're talking about the B, of course, B at the center of a current loop, like that. All right, so let me draw it real big here, like this. And then I use a way to tell you the front and the back that people don't like because it's a little bit like organic chemistry. I shade this one really dark here. That means that's the front side close to you, okay? It's not about bonds, don't worry. They don't know anything about physics. They use the word resonance completely incorrectly. There we go. Okay, so in 3D, this is the part close to you and that's the part far from you, right? Totally, you can see that, right? Do we just want to give the answer or do we want to do the integral? The integral's a lot easier. Let's do it. It's so much easier. Oh my God, it's so much easier. dB is, B is the integral of dB, which is the integral of mu naught I. There is current going around the wire. I made it go this way, right? Oh, well, is it capital or is it, oh, it's constant. Oh, God, I don't know what I do. There we go. Current's going around the loop like that. Mu naught I over 4 pi. And you see the key, what makes this easier, is here's ds, and here's r, and r is constant. We're going to call it big R. The r vector is always the same magnitude. So that means there's a lot less variables to deal with. Mu naught I over 4 pi. I'm going to put the r squared down here because it's a constant. And then ds cross r. So we won't do the, well, I don't know. Here's ds. Here's the r vector. They're always perpendicular. So all that weird cosine, sine, differential stuff is fine, right? So the keys are that r is constant and ds is always perpendicular to r, like that. So that means that it's just ds, magnitude is just ds. Magnitude of the unit vector r is 1, and the sine of the angle between them is also 1. So it's just ds. But what is d? Okay, so it's just ds. Right? That's all there is. Right? But now how do we integrate something going around a circle? We want to turn ds into an angle. We want to integrate around the circle. So around the circle, it would be equal to the integral. I guess we want to go from 0 to 2 pi. We want to go all the way around, right? Theta all the way around like that. Bunch of constants, mu naught I over 4 pi r squared. And ds is a little bit of arc length. Remember, a little bit of arc length is always r d theta. ds is r d theta. So this ds is r d theta, just from geometry. So maybe you remember that from last semester. Let's not go through and prove it. Better things to do. But you can see what that's going to do. R to 1. Mu naught I over 4 pi r times the integral of d theta around 2 pi, which is just 2 pi. Right? Integral of d theta is theta. Theta at 2 pi is 2 pi. Minus theta 0 is 0. 2 pi minus 0 is 2 pi. So again, we integrate in our heads here. And we get mu naught I over 2r. Right? That's b at the center of a circle. Draw it like that. Right? Not anywhere in the circle. Just the center of the circle. So these two formulas look pretty similar. B, a distance r from a wire, is mu naught I over 2 pi r. B, at the center of a circle, radius r, is mu naught I over 2r. It's kind of weird that the circle doesn't have the pi in it, and the wire does have the pi in it. Yes, the universe is weird that way. Yes. Also this, it's a variable r. You could be different distances from the wire for a single wire. Here it's a constant r because you have a finite ring. I mean, you could imagine a ring that can expand or something, but basically this has a set r. Okay? And it's just the field here. Now, which way is the field? If we drew it this way, oh, you could do ds cross r hat, figure it out, or you could just trust my rule. If one thing is curved and one thing is straight, which way is it? You might say, but I thought the field had to be curved, but here we want the field at one position. At one position, it's a vector, it's straight. And clearly the current is curved. The current creating it is curved. So here, the current is the curved thing, and the field is a straight thing, opposite from over there. Right? So we take our right hand and make our fingers move around the curved current, and the field must be up. So the field at the center is up, like that. Okay. And if you wanted further confirmation, you don't have to write this down for your notes, but let's think, what if we thought about all the little contributions? If we said, what if I zoom in real close to this wire, put my thumb along it, because now when I zoom in close, the wire's straight. The field inside, next to the wire, is going up. And the field outside the wire is going down. But I just care about the field inside the wire. Everywhere I go, the field inside the wire is up. Right? You can convince yourself of that. Therefore, if everywhere you go inside the wire, the field is up, it's all going to add up to be up. So there's even a way to get it, but to go from straight to curved straight. Okay? One thing's curved, one thing's straight. You can always get the answer, the direction that way. Can you show the right-hand rule for this field again? What does your integral on the first board have parameters from minus 90 to 90? Yeah, so minus 90 to 90 was like theta. If I put my ds at negative infinity, that's going to be minus 90. And if I put my ds at positive infinity, that angle is going to be 90. Go do that as an exercise. We'll see you never. Can you show the right-hand rule for this field again? I mean, it depends on, we did it like 5 times. So, I mean 5 different ways. So I don't know which way you mean. But the simple way is the current is going around the loop like this. It's in the front. So here I bring it out into space. You got your AR glasses on, right? So it's on the front, it's going this way. And in the back, it's going that way, right? So that's why I know that the B at the center is up. We only solve the B at the center of the loop. And here we solve the B outside of a wire. Okay. Can't see on left side. Can't see. Okay. You come walk by during the break. Let's see. So that's 2 fields. Two fields. Which variables will be given in a problem like this? Oh, who knows? We might vary the permeability of free space. I don't know. You never know. Here's an example of a problem we could give, okay? Superposition applies to the B field. So I'm going to set this problem up. I'm going to leave it during the break. You don't have to spend the break doing it if you don't want. You can think about it, and I'll do it real fast after the break. Here we go. Here's a classic problem. What is B at the center of the loop. And you say, oh, it's mu dot I. No, hold on. Wait till you see it. Here we go. Here's the wire. Like that. That's a circle. All right? What's B at the center of this loop, a radius R, if I is 2 amps and R is 10 centimeters? That would be a typical problem where you have to superpose some of these things. So I will do that one after the break. Wore you out. There we go. Oh, God, sorry. Just the fact that if you had to predict the direction of the torque vector based on the motion, that was the idea. There's that link applies.
Like how did the right-hand rule factor into that?
Well, the right-hand rule technically factored in because it's R cross S, or it's S cross F, and ds dt would be the velocity. I mean, the cross product is hard to explain why it factors in, but the right-hand rule does because the motion is your curvy fingers and your thumb is the straight direction of the torque vector. That's all. Yeah. I'm just telling you, it's not just magnetism, basically. It applies other places. All right, let's keep going. We don't want to miss the cocaine video. Okay, I forgot to show you that we can prove that this happens. So I said that the field going around a wire makes circles. So you've seen these pictures before, but you've never seen it live. You've never seen it live. Here's some iron filings around this wire. Check this wire out. Look at these iron filings. Look at that. It's robot dandruff right here, right before your eyes. Okay? And they're actually little straight filaments, but they're all different directions. So they don't look like they have a pattern, or as my kid used to say, a pattern. Okay? There they are. No pattern. So now I'm going to send a lot of current through the wire, and we'll see if they move or not. I think that's barely detectable, but you'll see a little bit of motion. Oh my God, that was sad. That was sad. I should have zoomed in. But there you can see there's a little bit of a circular pattern. Let's juice it. Let's crank this thing up. Come on. Come on. Oh, too much. Too much. But now you can see around the sides, they definitely took on kind of a swirling kind of a thing. I put on too much. I have trouble pulling back. Okay? But that's the idea. The field really is going around the wire. We'll look at another one of these in a minute for a better geometry that will make you go, oh. Okay, so now let's solve the problem of this. How do we find the superposition? Oh, I forgot to clean that off first. Oh well. Superposition. How do we solve this problem? Here we go. So what we say is we want the B field here. I mean, technically, this is just a iron loop, a wire going this way carrying current I, and a circle like this carrying current I. Even though it's a spiral in the same wire, the magnetic field doesn't care, right? It's two fields. So what we say is that B, if we call that point P, B at point P is the vector sum of B do the straight wire plus B do the loop. All right? So we just got to plug in those two values, and we've got to think about the fact that it's a vector. So are those in the same direction or opposite direction? I don't know. Let's figure it out. So first of all, we've got to figure out the field due to the wire, the magnitude. Mu naught I over 2 pi big R. Mu naught I over 2 pi big R. And you say, wait, I thought radius was for the circle, but here, the distance we are from the wire happens to be the radius of the circle. And it's a constant, so that's why I wrote it with a big R. Right? We have the formula to get the field everywhere, but you're asked for the formula, the field here, so we put in big R. And then plus B of the loop, mu naught I, same current, over 2 pi, over 2R. No pi, right? Okay. Now, what about the directions, though? Are those really going to add? Are they both in? Are they both out? Are they opposite? Let's see. For the straight part, thumb along the wire, hand, fingers curving. For the straight part, it's coming out. Very fortunate that I drew a dot there. It is a dot coming out. For the curvy part, the current, the way I drew it, hopefully you can kind of tell, it's going to go this way. Right, current this way, also out. Right, they're both out. Both. Check out that calligraphy for you. There you go. That was like, that's not how you spell both. Both out. Right, so we do just add them. And of course, it's annoying algebra. It's mu naught I over 2R times 1 plus 1 over pi. Over 2R times 1 plus 1 over pi. Right? Which isn't really helping you that much. But in the end, you'll get, if you do the numbers, you get 1.66 microtesla. 1.66 microtesla. Remember, always exaggerate your mu's. Because all we're doing is plugging in mu naught, 4 pi times 10 to the minus 7. I is 2, and R is 0.1 meters. And that's what you'll get. About a microtesla. So for the straight one, you looked at the direction of your fingers and the circle direction. Yeah. Because basically, for the straight one, the current is straight, and we know the field curves. Right? So current is straight, and the field curves. For this one, the current is crooked, or is curvy. We just want the field at one point. And at one point, a vector is always straight. Really, the field of a loop is like curving around and all this, but if you just want the center, then it's going to just be a straight vector. Yep. So that's how you would do it. How would I make this hard? How can we possibly make any variation of this? There you go. You could do multiple loops here, and now you got to put something in front of that B, right? An N, right, for every loop, right? Ooh, you could do like the Lululemon problem. You could go like this. What would that do? Ooh, yes. I don't own any, I swear. Okay. The final geometry. Let's just finish the geometries, and we'll still have time to do cocaine. Okay, here we go. So let's see. The video, obviously. All right, the final geometry we're not actually going to calculate because it's getting very complicated, and you have to do Maxwell's equations. So this one I'm just going to give you. But by now, you're going to believe me. You're going to have complete faith that it's correct because you've seen all these fancy calculations and because I'm going to show it to you. Okay? Here we go. Solenoids. That's the word I couldn't think of earlier. Stacked loops. All right? The solenoid. Here we go. If I draw the solenoid in real life, it looks like this. Right? It's just like a loop of what, it's like a slinky. Here you go. Here's solenoid. Oh, nice. Okay. So it's just like that. Okay. If we're going to make it ideal, you could think of them as individual loops. Right? It's really a spiral, and they're connected. And you do that in the real world because you want like the same current flowing through all of them. But in an ideal version, we could think of it like we could ignore the curviness, and we could say there's a loop like this. This is the cross section. Right? There's a loop with current in it. There's a loop with current in it. There's a loop with current in it, like that. And we'd say all the current is coming out here and going in here. So there, I'm using the vector notation to indicate the current. Okay? So you can see those are slightly different. These is a bunch of ideal loops with current moving through them for no good reason. I'm just telling you there's current moving in these loops. Really what you do is you'd have them connected as a coil, and it's almost the same thing. Okay? We could calculate the difference, but you don't want to, trust me. Okay? See what this is? Do you see what this is? This is not, right, this is just an ideal version of this. I'm seeing lots of faces going, what? I mean, that's just because I looked up. Okay. I'm not used to that. I should be. Okay, so let's look at the properties of this thing then. It's got a current. Either a current you think of going through the whole wire and therefore going through every loop, or you say it's got the same current going through every ideal loop. Same thing. Right? What else has it got? Is that a sideways point of view? Well, yeah, this is like a 3D cover of your junior high notebook point of view. Okay? You used to draw like, look at this 3D drawing, like stuff like that. This is like 3D. This is a cross section where they're individual loops. Right? This is a slinky. Okay? I don't know how else to say it. So it's got a current I, right? And it's got this important number, N loops per length. Right? N is in loops per length. It's equal to N loops per L. Okay? So usually, if you're talking about an absolute number, like a count, you use capital to say the count. If you're talking about that number per some sort of density, like per length, you use a lowercase, at least in my world, right? So N equals N over L, where L is like the length of the solenoid. Sorry, this got crowded. L is the length of the solenoid, and it has N loops. So you could characterize it that way. You could say, oh, it's a meter long, and it's got 1,000 loops. Or you could characterize it and just say, it's 1,000 loops per meter, right? 1,000 per meter, or 1 per millimeter, or whatever. So this is, as you can imagine, that's how you would characterize a solenoid. It's loop density, you could call it. I meant to look up the book's word. It's basically just a little n. Okay. What else do I need to characterize? Let's see. Is the direction you are looking at the slinky for that to be the cross section? I don't know if that was a serious comment. I mean, it's just a general slinky drawing. You can't really tell if it's this way or that way. If you need me to, I could say these are the front surfaces. I guess. I'm not sure if this is what you're getting at. But yeah, no, it's I don't know. Okay, let's move on. Office hours. I'm going to question my artistry. Why are there two heads on the phospholipid? Oh, no, that's completely unrelated. Who the hell is asking me that now? Oh, somebody's asking about the phospholipid. Oh, my God. Hopefully you're just being funny, but I'll answer it anyway because I'm professional. Why are there two heads on the phospholipid-looking thing when there's only one loop in the wire? Oh, this is a cross-section. This is a zoomed-in cross-section. Right? This is like metal wire. Zoom in here, like that. There you go. If I don't zoom it in, it's hard for me to put the dot there. All right? Wow, okay. It's not you, it's me. It's not you, it's me. Okay. Okay, so the real question that we care about is what is the field inside of here? And I didn't give you the radius yet, did I? Oh, it doesn't matter. This isn't my notes. It doesn't matter. The B, this is the magic thing that makes a uniform B. Solenoid creates a uniform B field. So just like two plates of charge created a uniform E field, the solenoid creates a uniform B. So if you'll permit me to show it in cross-section again. So now the wires are a little bit of an intermediate size, like this. Right? Here the currents are coming out. Here they're going in. Okay, just deal with it, right? That's basically the thing. I'm not going to draw the legs of the phospholipid. The B field, B equals mu naught in I. And that's all it is. The permeability of free space times the loops per unit meter, the loop density, times the current. Easy formula. But here is the amazing part here. It's constant everywhere inside this volume. Okay? It's not like this is just the central axis value and it gets smaller. Same value here as here. Same value there. And as soon as you go out, 0. Okay? It contains the magnetic field inside the loops. Wow. Are you sure? Yes. Here we go. Let's look at it. Let's watch it happen in front of our very eyes. So here's a loop. Here's, there we go. Now you're looking down one. All right, here we go. And let's put on the sprinkles. Yes. There we go. Okay. Let's put on the sprinkles. Would you like filings? Yes. And I need to not get them so dense that they're touching. Here we go. Oh, you can't see those. Okay. Okay. Oh, I didn't hook it up. Oh my God, there's electrodes everywhere. Oh, statistically, I really need to stop teaching because it's just a matter of time. Okay. All right. All right, maybe you can see those little guys. Here we go. Ah! You see how they lined up? Look at how lined up they are. Look at that one. Look how lined up it is. Look at it. Let's put on a little more and we'll zoom in. But the amazing part we're going to see in a minute. Now we're going to look right on the edge. And you're going to see that the field outside doesn't line up at all. Let's zoom in. Here we go. The stuff on the right is in and the stuff on the left is not. Do you see those little jump right there? Right? So these jumped and lined up inside the solenoid and these didn't care at all. Right? Because the field really does die the second you go outside the solenoid. It goes to 0. So if you want to come look at it after, I'll leave it nice. And it's just sort of amazing that even this crappy setup with these loops spaced 1 per centimeter, no field out here and a huge field inside. So solenoids are just really good at this. Okay, so I want you to believe me that the field outside is 0. Okay, so we're not going to drive that one. There's your formula: mu naught little n times I. So in a problem, we might say, a certain number of loops per meter, or I give you big N and big L. Okay, I lied. There's one more. There's one more field generation device, because that's 3, right? That's a wire. a loop of wire, and a solenoid of wire. And now we just got to do one more, which is a bar, a magnetic material. A bar magnet. Let's see. Oh dear. Okay, permanent magnet. And this is why it's so confusing, is all your experience is with these things that you buy at the store, you play with as a kid, and but their fields are so complicated you can't like write a little simple equation to describe them, unfortunately. But if you have a bar magnet, there's really only one thing I want to stress: north. It has a north pole and a south pole. Okay, and really, if you think of it as little loops, little atomic current loops, you would decide that the current must be going like that. If this is the outside facing you and that's the farther to the back in my 3D world here, you would decide that the magnetic field must point like this. Okay, that's sort of the definition. It's pointing from south to north. From south to north. All right. But then the trick is, I don't think I'm saying this backwards. The trick is the field goes from south to north inside the magnet where you can't get to it. The field you measure is the field outside the magnet that goes like this. Really, the field lines are loops. They always, the field vectors are loops. They always stop and start and go in a loop. They don't come off of anything because there's no magnetic charges. So if I had to draw this as a bunch of vectors, it would go like this. So if you're outside a bar magnet, it does this. And you'd say, oh, it goes from north to south. This is why the magnetic field of the Earth is upside down from what we think it is. Right? So we think the magnetic field goes from south to north. But we're outside the Earth's magnet. On the inside, it's going the other way. And that's why the south pole is actually the magnetic north pole of the Earth's magnet. Okay? So my main point is simply, when you're playing with a bar magnet, you're dealing with the field outside, not inside. Usually you're playing with it here because this is where the field is big. But if you think about the side, it's going the opposite of the north-south on the inside, and you can't access the inside. This is also, like if you have one of these horseshoes, why they use these horseshoe magnets. If you want a really big field, you put like the north pole there and the south pole there. And then you get these two things close together, and then it's bigger. So anyway, the third thing that makes, or the fourth geometry to know is just roughly what this looks like. If you have a bar magnet, you got a big magnet here, field on the outside. And we'll use that more when we get into NMR and stuff like that. We'll be talking about that a little bit more. But for now, just to be complete, I wanted to mention all the sources of fields. Okay, we have 13 minutes. Cocaine is only 4 minutes long, so we're in good shape. Okay, here we go. I'll keep erasing. Okay, so now we're done with the sources of the fields. Now we are to where we were supposed to be starting today. So we're actually in good shape. There's not that much to do. Okay. I mean, we got behind, I don't remember why. How did we get behind? I don't remember. Okay. So we talked about how moving charges create magnetic fields a lot, right? We talked mostly about currents creating magnetic field. But we also remember at the very beginning, our whole idea was that moving charges feel, and by feel, of course, we mean forces, magnetic fields. Okay? So now we're not making the field. We're just assuming a big field exists. What does the charge do? So maybe the whole world is happening inside some big solenoid, or maybe we're next to a planet with a big magnetic field, whatever. We're saying there just is a field. What happens to the little free charge? So here's the formula. Force on a free charged particle. And free just means it's just sitting there in the universe ready to feel a force. It's not part of something else. Okay, well, since the magnetic field is loopy and difficult, it of course involves a cross product. The force on the charge is the charge magnitude times how fast it's moving, or times its velocity vector crossed with B field. All right, so that's the charge. This is the velocity. Because remember, like I said at the very beginning, it has to be moving to feel this force. But a charge has to move to create a magnetic field, and a charge has to move to feel the force of a magnetic field. And here I'll label this, just as a reminder for later, this is an external B. right? It's not the one created by this charge. It's the one this charge is feeling. Just like a charge can't feel its own electric field, it can't feel its own magnetic field. Okay, so that is the super vectory sort of version. If we want to write that in terms of magnitudes, then you probably know by now that the magnitude of a cross product is like this. It's just all of the parts, QVB. There's magnitude, just multiply them, times the sine of theta. And theta between V and B. And whenever you talk about the angle between two vectors, it's always tail to tail. You draw them tail to tail and get the angle. Okay? I can bring this back up. We don't have to keep not using this side. Let's see. All right. And then the direction, of course, how do we get the direction? That's the magnitude. And the direction is from the right-hand rule. That's how you would get the direction for that. Right. Oh, I don't want to use that one. All right. Okay. So let's see let's predict a few directions and let's think about the trajectory you would get. With plenty of time. Okay, so let's think. Let's do a few practice ones here. Let's draw magnetic field this way. So you see I'm drawing a uniform field, kind of like we did with electric fields. A charge, a positive charge Q that way, and a vector, a velocity vector up that way. Which way would the force be? So think about it for a second. Attempt your right-hand rule. You have to do the cross product now because nothing is curvy yet. Right? Must do cross product. All right, it's V cross B. The order matters. You got to do your fingers on the first one and curve to the second one. So V cross this way. V cross B into the board. The force would be into the board. What if I draw this? You'll say, he's lost it. I don't know. It's gone all Pollock on us here. Here's the B field into the board. That's how you draw a uniform field into the board. You're welcome. And I have a proton here. No, I have an electron here. Ooh. And it's going that way. What is the force direction on the electron? Oh dear. So V cross B to get started. B. And I want to curve into the board. Cross B. Into the board. You'd want to say that way, but you put the charge here, not the charge magnitude, you put the full charge. So there's a negative sign there, it flips it the other way. So because it's an electron and it's negative, it's down. Which clearly I didn't think about because I wrote the electron word in the wrong place. So many more things going on here than you realize. F, yeah, that way. So later in your notes, when you think, wait, why is it that way? It's because it's negative. All right, so you got to think about that. Yeah. So, that's all it is. Cross product, more cross products. Now we want to think about what kind of motion will this create? Ah, yes. How will this make it move? All right. How will it move? My phone is gone. Okay. Okay, so let's look at free charged particle motion in a uniform B. All right? So here's a uniform B. Like that. And again, into the page, right? And I've got a particle here, positively charged, plus Q, and it's moving like that. V. Okay. There it is. Which way is the force going to be? V cross B. And it's positive, so it's up. Feels the force this way. How's it going to move? 125 is a prereq. It's got a velocity to the right, but it's accelerating up. It's going to move kind of like this, right? Kind of like a gravitational thing pulling it up instead of down. But now, what is it doing? Now, it's got a velocity that way. V cross B. Now the force is turned a little bit. Got turned there, and it's going to curve some more to here. Now there's V. V cross B, like that. What is it doing? Oh no, let's see. It's going like this. There. Well, let me stay there so you can see the full circle. There you go. Right? It's going in a big circle. Right? So a charged particle moving in a uniform field, if it's moving the right way relative to this field, will feel a force that constantly turns it into a circle. It doesn't have to go in a circle. If it was going this way, the force would be 0. Right? But if it has any motion in the plane perpendicular to the field, it'll have a force vector that constantly turns and makes it go in a circle. Okay? We're not going to prove that mathematically. We're just going to say that it's true. I mean, we're just going to give you the idea from what you know about circular motion. Somebody says, maybe one of mine is wrong. Should the force vector point to the top left? No, because it's an electron. V cross B. See, yes, it's negatively charged. I think I mentioned it. Okay, so now what we're going to do is we're going to say the force and the acceleration are perpendicular to V. And that is how you get circular motion. Right, that is the hallmark of circular motion. Something going in a circle has an centripetal acceleration and some speed that way. Right? This thing's speed is not changing because we can't do any work on it because force is perpendicular to motion all the time. Okay? So let's just write the one little equation we need. Let's then say, okay, well, QVB must be equal to MAC, but MAC is V squared over R. Right? So we could say that the F, the magnetic force, is the centripetal force in this case. Could say that. And you could cancel a V. Right. That's about it. And you would find that the radius of the circle just depends on a few things. It depends on the mass and the speed and the charge and the magnetic field. All right. So if you have this uniform field, this thing will go in some big circle. But if I slow it down, it'll go in a smaller circle. It's because it's proportional to V, right? But if I speed it up, it'll go in a bigger circle. Or if I give it more charge, it'll go in a smaller circle. Basically, the bigger the magnetic force, the larger the pull is and the smaller the radius you get. And then vice versa. Okay? So any charged particle moving in a uniform field makes a circle or it makes a spiral. If it's got a little bit of a component this way, it'll just drift as it makes a circle. It'll move in a spiral. Okay? So this is the basis for mass spectrometry. Do we want to watch it now or next? Okay, let's watch it now. Okay, so there is an urban legend out there that all money has cocaine on it because people did so much cocaine in the 80s. Okay? And it was always mixed in and however they use it with drug paraphernalia. So in principle, you can prove this with mass spec. If you do mass spec on any dollar bill, okay, maybe not a single, 20s and above, it has cocaine on it. Your money has cocaine on it. So I will leave it up to you. I will turn it real loud, and you can watch this as you're packing up. Very charming Englishman here is going to tell us, show us how a mass spec works. I'll talk about the mass spec next week. Oh no, drugs are the problem. Oh my God. Here we go. So enjoy Kyle, or whatever his name is. Let's see. And we have no audio. Late night. And there it is. Cocaine on the banknotes.
It's frequently reported that our banknotes are laced with Colombian spiders. So are you really carrying around an illegal narcotic in your wallet? We're going to find out. All I need is some cash.
He's going to explain how it works, too.
Cheers. You can't smell it? You can't taste it.
Can't taste
So how do we find out? Well, we can use a mass spectrometer. Follow me, I'll show you how it's done. We can't put the note directly into the spectrometer, so we need to extract all the organic material off the note.
You're going to have a chem lab nightmare. Hold on. Little flashbacks. Oh.